long time, and I finally think I got something, which is the relationship between the gravity conjecture and, well, in holography. So, we all love the swampland here, but I would say that the swampland is not equally swampy. Not all of the swampland is equally swampy, by which I mean that we understand different parts of the swampland, different parts of the swampland constraints with different degrees of, certainty. So I would say, I think it's fair to say that most of the swampland is based on evidence, okay? And this is amazing. We have very non-trivial evidence in a lot of examples, and furthermore, sometimes, like for instance in Ernest's talk, or also in Timon's talk on, I think this afternoon, there are sometimes whole classes of models in which you can use rigorous theorems to prove that these conjectures hold rigorously within these classes of models. And this is actually amazing. However, there's, from my point of view, even there's a few swampland constraints for which you can make an even more general argument, okay? By which I mean all these examples in some classes of models, to prove the swampland conjecture in these cases, you assume something about the UV. You assume it's a theory or something about string theory. But there is one case, for instance, which is in ADS, in which I can actually make a very general argument, which is, to me, very compelling, which is, well, the statement that there are no global symmetries in ADS. It's basically the same thing as having Noether's theorem in the dual CFT. There's no strings, there's no SUSY. As long as you have a CFT dual, this is a very good argument. Maybe I should have not said rigorously proven, maybe that's too grandiose, but you get the point, okay? So, if most conjectures are based on evidence, and then some of them are rigorously proven, I would say that the best conjecture is the weak gravity conjecture, because you have not one or two, but three proofs in just one workshop. So both Gary and Grant discussed proofs of the weak gravity conjecture, and I will be doing the same in a different setup, okay? Hopefully this is work that will appear very soon on arXiv, maybe this week, or hopefully at latest early next week. And just like any other proof of anything, you have to take some assumptions, right? So this is my list of assumptions. Basically, I will assume holography, meaning all my statements will be restricted to ADS, and I will use the magic of the CFT to get something interesting. And furthermore, I will so my ADS theory will have some effective field, there will be some effective field theory there. And the gist of holography is that you can use these things that you compute in the bulk in this effective field theory to get predictions about quantities of interest in the CFT. And in the large and limit, the semi-classical result gives you the leading piece of the actual CFT thing that you want to compute. So I will be working this approximation, which is in any case the approximation you always have in holography. Okay, I will assume that the semi-classical bulk effective field theory is really giving me the leading end dependence of quantities of interest in the CFT. So to remark, I'm using actually one of the usual crutches, which is ADS, but I don't use others. At no point in the argument will SUSY explicitly show up. It might be there. I'm okay with it. It just will not play a great role in the argument. And, or even, at no point I will use explicitly stringy features. It might very well be that all consistent quantum theories of gravity in ADS are just string theories, in which case all of this is in string theory, but at no point I will use it explicitly. And in fact, the result I will get, it's kind of similar to the original black hole heuristics. The original black hole heuristics basically told us that, in the end, the weak gravity conjecture is about having extremal black holes to decay because of entropy reasons. I will get a similar statement, which is that black holes have to decay because of entanglement entropy reasons. And more concretely, I will present a rigorous quantum information theorem, which when applied with these assumptions, leads to the conclusion that there are no exactly trivial black brains with some other hypotheses that I will mention later on. Okay? So, this is the arena. And then let's start with the argument. So I will, like I said, I will try to argue by contradiction. I will have a look at an effective field theory, at a hypothetical quantum theory of gravity in ADS, which doesn't satisfy the weak gravity conjecture, and see what goes wrong. You will see later on that the argument is actually pretty general, so it will work for many theories, but I think it's good to just focus on one for concreteness, so let's just focus on Einstein-Maxwell ADS. You could possibly also have charged matter, as long as this matter doesn't satisfy the weak gravity conjecture. Okay, so this theory has black brane solutions. They only exist with ADS asymptotics. They're just like your familiar Reisner-Rosen black holes, but with a planar horizon topology. So they're like a black hole with a planar horizon. Other than that, they're pretty much like normal Reisner-Rosen black holes. They have a temperature, they have a gauge field turned on with this quantity, which is basically the boundary value of the gauge field, will play a role momentarily. They have a horizon, and there's an extremality bound. So, and basically the brane at 0 temperature, it's the brane with extremal radius, which is furthermore finite, okay? So, black branes. Keep in mind the black branes because they are the main player here, okay? So, what I will do, basically, I will compute two things using the bulk perspective. I will compute something about the thermodynamics of the CFT using the bulk perspective, and I will also use it to compute holographic entanglement entropies in CFT states which are dual to black brane backgrounds, and get a contradiction. And just to be sure, because I'm looking at flat black branes, this is the CFT in flat space, okay? So, first thing you want to compute, thermodynamics. This is actually the first thing you do in holography. Indeed, whenever you have a valid Largen limit, turns out the partition function of the CFT is a sum over saddles in the bulk theory which have the right boundary conditions, okay? There's a whole story, but basically you can tune boundary conditions in ADS to introduce deformations in the field theory. It turns out that the black brane that has a temperature, a chemical potential that I was describing before, it's actually the dominant saddle in the sum for the CFT when I look at the CFT at finite temperature beta, and I introduce one particular deformation, which is to deform the CFT by a chemical potential. So in the bulk, I have a gauge field. In the boundary, I get a conserved charge, which is Q. And basically, this black brane is telling me about thermodynamics of the theory with this deformed chemical potential. This deformation breaks conformal invariance, breaks Lorentz invariance, but as a quantum theory, like the kind of theory that condensed matter people look at all the time, is completely fine. And it leads to interesting predictions which have puzzled people for a long time. So for instance, if you take the limit of 0 temperature, because you get that black brane with a finite horizon, you get a finite entropy, which is weird. Basically, this is the holography is predicting that the dual theory has a highly degenerate ground state with a volume degeneracy. That's just not something that happens in normal systems. But anyway, and then another thing, which is actually the important thing here that we can compute from this black brane perspective, is the heat capacity of the CFT, which turns out to be proportional to temperature at low temperatures. Okay? Keep that in mind. That's the point to keep in mind. The black brane tells me that the heat capacity is linear at low temperatures. The other thing that I want to compute is entanglement entropy. So, you know, the usual deal, you have some field theory, and then you introduce some surface, which partitions the space where the field theory lives into regions, and then you want to compute the entanglement entropy between the degrees of freedom inside and outside. Now, in general, this is very complicated, but again, in a theory with a Largen limit, so again, notice that I'm constantly assuming that the Largen limit is good. Ryo and Takayanagi told us how to do this computation. They told us what the leading piece of the entanglement entropy is. It's basically you have to take this surface in the boundary, extend it into the bulk, and then the area of this bulk surface is basically entanglement entropy that you're looking at. Now, one thing that people like to do is to look at how the entanglement entropy behaves when you change the size of this region. You can make it small, you can make it large. When you make it very large, typically you have universal behaviors, and then, for instance, then it can happen that the entanglement entropy scales as the volume of the boundary region, not the bulk, the boundary region. This is what happens for a generic quantum state. Or it can also scale as an area law, okay? So this is typical of ground states of quantum field theories, okay? So, bottom line of this slide, I'm gonna use Ryo Takayanagi. And now we get to the main point, okay? Which is this theorem, which I found in the literature. I put in a blue box because this is a rigorous theorem. It's proven, so it's protected from all the conjectures by the boundary of the box, okay? So this theorem tells me that as long as some assumptions hold, then in a theory which basically it tells me an upper bound on the entanglement entropy of ground states. So this is a quantum field theory which has some ground states, possibly degenerate, but the entanglement entropy of translational invariant ground states scales as a subvolume. So basically this here has a parameter, gamma, which is set to 1, which is what we get from the black brane. And it tells us that the entanglement entropy in this theory can scale. According to this theorem is okay with the entanglement entropy of a ground state growing faster than an area, but it cannot grow as a volume, okay? So, because this is the main point, I should be careful that, and I want to apply this theorem to the CFT dual, I should be careful that the hypotheses hold, okay? First of all, this is a theorem for lattice systems, but that's okay, because whenever you compute entanglement entropy, you have to regularize the CFT. It talks about local Hamiltonians, which in condensed matter language means nearest neighbor interactions, and this is ensured by locality. The Hamiltonian that I have is the integral of local fields, so when I regularize on a lattice, that means that you can at most have interactions with the nearest neighbors. And then, yes, I have polynomial heat capacity, which was one of the assumptions of the theorem. We're missing one thing. We're missing a translationally invariant ground state. Now, I believe that it's possible to do this with just one copy of the CFT. It's a problem in quantum information, which I haven't solved yet. Maybe it's possible, maybe it's not. Here, I will take an easy way out, which is instead to consider two copies of the same CFT and put them together. From the point of view of the theorem, this is totally irrelevant. I just doubled the number of degrees of freedom per point of the lattice, so whatever. The theorem still applies. But then, in this case, I can explicitly construct a state, the thermophile double state, which in general is not it depends on some temperature-like parameter, beta. It usually is not it's usually not a ground state of the theory, but at zero temperature, precisely at zero temperature, it becomes a ground state and is translational invariant. So this state satisfies the hypothesis of the theorem. The good news is that it also has a semi-classical Bowl description, and it's the same black brane that we have been talking about, only extended to both sides. So we've been talking about the black brane up to the horizon. If you consider the maximal extension of the space-time, it has two boundaries. So these are the two copies of the CFT that I was talking about. And well, this is a very standard picture that the thermophile double state is dual to a wormhole, to the eternal wormhole of this kind. So I can compute entanglement entropies for this state, which satisfies the hypothesis of the theorem in this picture. And in fact, because it's translational invariant, I will just do it at t equals 0 at this particular time slice. So let's compute the entanglement entropies. This actually was done by Andrade, Fischetti, Marov, Ross, and Rosali a few years ago in exactly this system, and they find something interesting. So here in this picture, you have the conformal boundaries on the left and the right. Here I've tilted them sideways, so this is one CFT, this is the other CFT, and this is the horizon. And I've included one transverse dimension, which was suppressed in the previous diagram, okay? Now, so if this is the endpoints of the entanglement surface, basically what you see is that there are two surfaces that you can write down that they are competing to give you the entanglement entropy. Whenever this happens, you're supposed to take the one with lowest value of bulk area. It's kind of confusing because there's bulk areas and volumes and boundary areas of volumes. I'm talking about bulk here. You are supposed to take the one with lower A. So if there was only the blue curve, we would get an area law. If there was only the red curve, we would get a volume law. But it turns out that at zero temperature, the blue surface has a divergent area. So it never is contributing. It never is dominating the entanglement entropy. The entanglement entropy is always dominated by the red curve, which predicts a volume law. Okay? So then we get a contradiction. We found a state which satisfies all the hypotheses of the theorem, and yet holography is predicting a volume law for the entanglement entropy. So that cannot be. We screwed up at some point. So I've been assuming validity of the Larsen framework, of the semi-classical calculation all throughout the computation. For me, this is an assumption. So I will just assume that that this is good. And indeed, sometimes when the bulk analysis is not working, you can check, because you can compute quantum corrections, and you see that they start competing. It doesn't happen here, okay? So maybe sometimes people don't like the fact that all these arguments is at zero temperature, so I send in data to infinity and whatever. I think it's perfectly fine to work at zero temperature. I don't see any problem. But in any case, I can repeat the analysis in a limit. it's of course more convoluted, but it also works out in the same way. So the thing, of course, that I want to conclude is that maybe the effective field theory, which is all the predictions that I get here come just from the effective field theory in the bulk. That's the nice thing. So maybe the problem is the effective field theory that I've been using, which was Einstein-Maxwell. In Einstein-Maxwell, the partition function was dominated by this black brane, which was stable. I mean stable in the sense that there's no other black brane with a lower free energy, okay? So maybe the problem is a theory which leads to exactly stable black branes, which then dominate the partition function. So what I conclude from all of this is that this quantum information theorem suggests that, in general, electrically, in ADS, only in ADS, this is important, electrically charged extremal black branes must be unstable. And by unstable, I mean that there should be some other saddle with lower free energy. There's a fine print here. The fine print is that, of course, we should get a polynomial low heat capacity, but this is very generic because the linear behavior that I mentioned is actually related to the fact that we have an extremal solution with a near horizon ADS2 geometry. So it's pretty generic. This is why I said that even though I made the argument for Einstein-Maxwell, I think it's more general. Okay, so we have a problem. How do we fix it? Whatever deformation, whatever way you find to ensure that the black brane is not stable works for me. But the simplest thing that I know of is a version, of course, of the weak gravity conjecture. You can introduce some charge fields in the bulk, and then basically, if you make sure that this equality holds, which is like an ADS-corrected version of the weak gravity conjecture, then the black brane that was giving you trouble, which was a low point it was a minimum of the partition function, now it becomes unstable, and it's not the dominating saddle. There's a new saddle, which people have studied, and has no horizons. If it has no horizons, I don't get in trouble with any problems, okay? With any quantum information theorems. So that solves the problem. Now, in the other two weak gravity proofs presented in this conference, it's about higher derivative terms, okay? Now, it might very well be that higher derivative terms also fix the problem here, but if so, I don't see quite clearly how it happens, because I can make this argument. In this argument, this chemical potential mu was a free parameter. I can take it huge. If I take it huge, that's a huge black brane, and I can basically, and because all of the things that I'm computing are effective field theory things, I can make any higher derivative terms that you want, which are suppressed by some UV scale. I can make them, they seem to be arbitrarily unimportant. So it seems hard for me to see how you get this with just higher derivative terms. I would like to mention that you can also get a connection with a much more well-known quantum information theorem, which basically says that if you have a quantum state in which all correlators decay exponentially with spatial separation, then you must have an area law for entanglement entropy. Now, there's no talk about ground states or whatever here, so it's just the black hole. And then, basically, if you check this, then you get this. In the black brane scenario that we were talking about, turns out that you can check that this happens for some correlators in the world line approximation, which is good for operators with high dimension. Because I cannot, or I haven't checked for all correlators, this is not as solid an argument as the one that I presented before, but I think it's still appealing. And, this all rings a bell with the ER-EPR story, because the reason why we are violating the quantum information theorem is because the blue surface 2 slides ago had an infinite length. And it has an infinite length. Basically, it's the same as saying that the wormhole connecting the two sides at zero time has an infinite length. So in ER-EPR, you always expect to have entanglement dual to a wormhole. And here we have a very entangled state, and it's dual to a wormhole, but the wormhole has an infinite length throat. So, maybe there's some connection there. Okay, so this is the bottom line. I found some quantum information theorem, which when you apply and take seriously holography leads to the fact that there should be no exactly stable electric black branes in ADS. Effective field theories that predict this, they are sick, the simplest, and in fact the only way I know of fixing them in this context is the weak gravity conjecture, the mild form of the weak gravity conjecture in ADS. But to me this is not the main point. so we have an argument for the weak gravity, that's great. The point is that if all of this works, what we've found is that maybe we can use entanglement, theorems about entanglement in the dual CFT to get Swampland constraints. So maybe we can check all the constraints, basically take whatever effective field theory that is violating your favorite conjecture, try and get it to produce some black brains, which violate this theorem. And maybe you can check previous conjectures or even prove new ones. And well, this is all by now. For now, this is all very ADS. It's all very ADS restricted. But maybe if we find a way to compute entanglement entropies in general, in more general spacetimes, you could imagine that maybe you could extend the arguments to those other cases. Okay, so that's it. Thank you very much.
Interested in supersymmetry per se, but if you are, namely, we know that there are extremal black holes which are absolutely stable.
Yes.
How does that work?
So this is actually one of the frequently asked questions. It turns out that in ADS, so if you only have electrically stable, electrically charged black brains in ADS, in this case, the extremality bound is always above the VPS bound. It's kind of like what Tom was saying. So you never find black brains in ADS, like the kind of objects I'm talking about, which are BPS and therefore stable. So there's no contradiction in this case.
Oh, but shouldn't you be modifying the weak gravity? I think that the form of the equation will change in ADS space. Have you taken that into account or not?
This form, yeah. So
if you include it, then the BPS bound should be, the supersymmetric bound should be saturated, right?
No. So you get the. So this is actually it's discussed in the catastrophic holography paper. So it's an old story. You have a BPS bound, which is still linear in charges, and still there are no extremal black brane solutions which are only electrically charged. If you include magnetic charges, then you can get extreme. You can get,
so let's talk about that.
Exactly. And so if you get magnetic charges, then you can have exactly stable blah 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 BPS black hole solutions. But then you should ask yourself, what are you doing? Because a magnetic charge can be understood from the CFT point of view, and it turns out to be the same as introducing a background magnetic field. A background magnetic field, there's no way to get a background magnetic field without a position-dependent vector potential, which violates one of the hypotheses of the theorem, which is, the theorem that I mentioned is only about translational invariant Hamiltonians. So it's again okay.
Yeah, I had a technical question. So one of the assumptions of the theorem was that the heat capacity should be polynomial in the temperature, which was fine for one copy of the CFT because the heat capacity was linear. But when you go to the thermal field double, you have a Hamiltonian which is sort of plus the usual H for one copy and minus the usual H for the other.
Oh, sorry, yes, I didn't discuss this point. I'm actually taking a Hamiltonian which is Hamiltonian in one CFT plus Hamiltonian in the other CFT, okay? I'm free to pick whatever Hamiltonian I want in the bulk. If I want time evolution to go upwards in both slides, okay, the point is, there are two Hamiltonians that you can take with the thermal field double thing. Both times upwards, or one time upwards, one time downwards. If you take one time upwards, one time downwards, any thermal field double at any temperature is actually an eigenstate of that Hamiltonian. But this is not what I'm doing. I'm taking the other one, the one that takes two times upwards, and then only at zero temperature, which is the one I'm looking at, this is an eigenstate of the Hamiltonian. It's like if you look at the standard thermal field double picture, forget about chemical potentials, the same happens, right? The zero temperature thermal field double is just vacuum times vacuum, which is, of course, an eigenstate.
Sorry. Okay. So, question was following up on Kamran's. Something that's special about cases where you have the BPS bound is that, at least in flat space, the black hole extremality bound is modified by the presence of a massless scalar field.
Right.
My understanding is that you have not incorporated massless scalar fields into your...
This must be different, yes. There's no scalar. I think it's an intrinsically ADS thing. You just work out the solutions, and this is something which is well known in supergravity. Like you.
Any other questions, comments? No, we can stick it in.
Thank you.